So, hello everyone. It's a pleasure to introduce Bjorn Emonts, who has been visiting this week. So I will summarize very briefly his curriculum. Bjorn did his PhD at the University of Groningen in Holland. He was a postdoc at Columbia University, and then he moved to the Australia Telescope National Facility with a Bolton Fellowship for 4 years. He came then to work at the here Center for Astrobiology with a Marie Curie postdoc, and then he was hired here. So you were 4 years here in total?
4 years.
Almost 4 years. So he's very well known to many of us. And currently he is at the National Radio Astronomy Observatory in the United States, in Charlottesville, as research staff working for the CASA user liaison. So he's going to talk about the high-redshift universe and molecular studies. So, all yours.
Thanks, Montse.
Okay, thank you all for coming here. Is the microphone, this is enough sound, I guess? This will do? Okay. Well, thanks a lot, Montse, for the nice introduction. It's a real pleasure to be back here. Like Montse mentioned, I worked here for 4 years, so it's great to visit again. And thanks to the organizers of the seminars for inviting me to give a talk. So today I'll talk about the global molecular medium around high redshift galaxies. Of course, I'm not doing this research alone. There's a bunch of people involved. I don't mention all of them here, but the most important ones, of course, Montse. There's also Matt Leonard, who's in Paris, Helmut Dennebauer and Jim at the IAC in Tenerife, George Miley, Carlos de Broek. We started some recent collaboration with a group of Xavier Prochaska and Shanghai. So the global molecular medium around distant galaxies. The title is Light Up the Darkness. So basically I have one question that I want to address in this talk. And the question is, are we missing a large fraction of cold molecular gas in the universe? Probably most of us know very nice imaging of high redshift galaxies. The microphone seems a bit... I could talk a bit louder, but I think they need the microphone for the recording. I think it's working. It's working now, right? You can hear me well, right? Yeah. Okay. So in the high redshift universe, typically if you look in the literature, what you see, if you look at high redshift molecular gas, is blobs of emission right where you see star formation. And there are some studies that have done higher resolution observations, as work by Tacconi et al. Or by Hodge et al. Who actually saw a nice molecular disk in high redshift. But you're talking about scales of 10, maybe 15, 20 kiloparsec at most. We know that at high redshifts, galaxies have much larger gaseous nebula around them. These are so-called Lyman alpha halos. So the most massive systems have these giant halos of ionized gas. And these large halos, they can be up to several hundred kiloparsec in size. Right? So even a few decades ago, in the 1990s, early 2000s, people found these large Lyman alpha halos around radio galaxies. And Emonts has done quite a bit of work on that as well. Recently, these large Lyman alpha halos seem to be rediscovered. Basically, the introduction of new facilities like the Keck Cosmic Web Imager and MUSE, they are allowing to really trace Lyman alpha emission on huge scales. There's even studies that link these large Lyman alpha halos to filaments of Lyman alpha emission that probably even extend down to the cosmic web. So there is a lot of attention for Lyman alpha emission in the environment of galaxies to scales much larger than a kiloparsec. These things can be hundreds of kiloparsec in size. The problem with Lyman alpha emission is that we cannot trace gas at a temperature lower than about 10 to the 4 Kelvin. Right? So all this gas in this environment is pretty warm. This is not the raw material that forms stars or that feeds galaxies. So we really need to go to lower temperatures in order to understand how this gas is actually affecting the evolution of galaxies within these large halos. Now people have done some work on, for example, quasar absorption lines. So what they do is they look at a distant quasar, and the quasar basically shines through the halo of a foreground quasar. And people have found gold metal-enriched gas on scales of halos, so hundreds of kiloparsec scales. But really what we're interested in is tracing down to molecular gas. The question is there molecular gas on these large scales in these halo environments? Because really, if you're tracing the cold molecular medium on 10 to 100 Kelvin degrees, that's really the raw material that forms stars and feeds galaxies. So the question is, do we see any of this molecular medium at high redshift on large scales? And I hope to convince you in this talk that I think we have evidence that we start seeing this. We have missed this in previous observations because we haven't really looked for it. Okay, so I'll give you a little bit of introduction to get a bit of an idea why it's important to study molecular gas. We all know that molecular gas is basically the raw ingredient for star formation. So if you study the molecular gas, the cold molecular gas, you get an idea about how galaxies are formed. Right? Now the problem with molecular hydrogen is that it's very difficult to detect directly. You really need an instrument like James Webb to see warm molecular gas, H2, directly in high redshift objects. Now luckily, we have a few very bright traces for molecular gas. So the most used one is carbon monoxide. So carbon monoxide is very abundant in molecular clouds, the most abundant molecule after H2. It's very stable and it's very bright. So people can trace carbon monoxide all the way out to the edge of the universe. And actually with the arrival of ALMA, there's different molecular traces that are now available as well to trace molecular gas in high redshift objects, in particular atomic carbon and ionized carbon. So if you're talking about CO, it's important to keep in mind that the CO transition consists of basically fundamental transitions here. The ground transition is at 115 gigahertz. The higher transitions are roughly multiples of those. Now, if you have various transitions observed in CO, you can fit these nice models and you get all kind of information on the physical properties of the gas. But often you only have a single transition to work with. Now, it's important to keep in mind that the critical density of molecular gas roughly scales as this J factor to the power 3. So that means if you go to higher CO transitions, you're basically tracing denser warmer molecular gas in star-forming regions, in AGN regions. If you want the best overview of the overall molecular gas content, including widespread emission, you really want to go to the lowest transitions of CO. Now, traditional millimeter instruments, for example, like ALMA, they have a hard time tracing the ground transition of CO at high redshift. I show a plot here where you see redshift plotted against CO transition that can be observed. And you can see here that ALMA, as well as ERA, for example, they have trouble tracing the lowest transitions, even up to slight redshifts here. So really, if you want to go to high redshift, you really need typical centimeter instruments like ATCA, which is the Australia Telescope Compact Array, or the Very Large Array to really trace these lower transitions of scale. So today I'm going to show you actually some results of several galaxies that we observed, several of these massive galaxies with large time and alpha halos, using all these instruments here. Okay, so I have a short video here to introduce the first object we're going to look at. So the first object is called the Spider Galaxy. And the spiderweb galaxy is basically a massive galaxy information at a redshift of 2. So this is real data. I'm zooming in a region of space around here. Well, basically, a dozen galaxies are coming together. So this is a galaxy information which is surrounded by a huge protocluster system. And you can see here in the middle, this is called the spiderweb galaxy. This whole region will eventually evolve into a single giant cluster elliptical. But it's a very interesting region. It's one of the best studied high redshift targets, maybe even the best studied high redshift targets. You see here HST data, I believe it's in total 20 orbits. So this is the HST imaging here. This is a 2-color imaging. It's made by George Miley and his team. And you can see here there's dozens of galaxies in the center of this protocluster. But if you look carefully, all between those galaxies, you can actually see some blue fuzzy light. So I'll get back to this later. A team by Nina Hedge in 2008 actually found that there's star formation all between the galaxies in the circumgalactic medium. So we observed this system with the Australian Telescope Compact Array to observe. Well, let me first show you this. Sorry, I changed the color scaling a bit here. I want to show you the giant Lyman alpha halo that surrounds this system. So this is about 250 kiloparsec in diameter. And in red, you see a powerful radio source. Right? So we observed this system with the ATCA. And what we found was this large reservoir of cold molecular gas with a total size of about 70 kiloparsec. And again, this is much larger than what you typically see in the literature. We have typical sizes of 10, 15 kiloparsec at most. So one thing you can see in the plot on the right is that the velocity dispersion of this gas is actually low compared to the velocity dispersion of these galaxies here in the halo. So this already tells us that a lot of this molecular gas is not inside the galaxies. It's really in the medium between the galaxies. It probably had time to relax and cool and settle in this environment. So here you see the channel maps of the CO emission. Basically what you see here is the CO emission at different velocities. So it's not an optical IFU, but here you see the different velocities. And you can see that the CO emission indeed doesn't seem to peak on top of any of these galaxies, but really in between galaxies. So it's another indication that what we see here is a large reservoir in the circumgalactic medium between the galaxies. And in fact, if you look carefully, the brightest peak of the CO is found in these channels here. And actually the peak in CO is aligned along the radio jet. I won't go into this in detail in this talk, but this probably tells us something significant about cooling in this environment. Some collaborators of mine, Goldberg and Matt Leonard, they actually found water at the same location along the jet. So water is an important cooling line. They didn't find any water in any of the galaxies or in the radio galaxy, but more in the halo along the radio jet. So this really suggests that the radio jet is somehow involved in local cooling processes in the halo. Again, I won't have time to go into detail here, but it's quite interesting with respect to the large reservoir of gas that we see. Okay, so we followed this target up with the VLA. Of course, we wanted higher resolution with the VLA. So we observed the system with VLA in D plus C configuration. And what we saw was the blob of emission right where we have the radio galaxy. So this is typically what you expect at high redshift. If you look in the literature, you always see these blobs of emission there where you have the star formation. But we only saw 1/3 of the ATCA flux in the VLA data, unless we really heavily taper the data. So I'm going to show you a bit of a technical plot here, but quite an important one for anybody that wants to observe in the radio arm or other millimeter interferometers. So basically what happens with a millimeter interferometer, let me show you another plot here. Basically an interferometer acts like a filter. So the way an interferometer works is you have a whole number of baselines, basically antenna pairs. These antennas look at the same source. Once there's a path-like difference between the antennas. So that means that the signal coming from the source is actually either in or out of phase on a certain baseline. And by combining all your baselines and scanning your source through Earth rotation, you basically build up an image of the sky. Now the problem is, if your antennas are separated too far, that means that very extended emission will be completely resolved out on your baseline. And basically that's what you see here. This is our data from the VLA in dark blue and from the ABCA in light blue. And I've got baseline length versus the amplitude that we observe on a certain baseline. Now if you would have a point source, you get fluxes in all baselines. But you can see here that very quickly the longer baselines resolve out the emission. So this emission is only visible in the shorter baselines, which must mean it's very extended emission. Right? So this is another indication this gas is not just in galaxies, it's really spread on large scales. And this is actually a problem in millimeter interferometry. A millimeter signal is very easily resolved out, especially if you go to a 1 kilometer baseline, for example. You're looking at CO1 to 0 ratio 2. It's already resolved out on scales of 14 kiloparsec. And if you go to ALMA operates at higher frequencies, so the actual baseline length in terms of number of wavelengths gets larger. ALMA even resolves out molecular gas on even smaller scales. So if you're interested in using ALMA, and you're just using ALMA for tracing gas and star-forming regions, you can push to higher resolution. But if you want to use ALMA or any other millimeter interferometer for tracing very extended gas, you really need to push the instrument to the lowest possible resolution. So really ultra-compact array configurations. And I'm convinced that's one of the reasons that we really haven't seen those very large reservoirs of molecular gas at high ratio. Okay, so we found this enormous reservoir of gas spread across about 70 kiloparsec. On the same scale here, you see the deep HSD imaging again. And I mentioned before, there's all this diffuse emission between the galaxies in this region. So this is basically this is star formation within the circumgalactic medium. This was determined in 2008 by Nina Hedge and collaborators. So we now basically found this enormous reservoir of molecular gas that's driving in situ star formation in the circumgalactic medium. And just to show you that all the numbers work out, if you plot the star formation in the CGM versus the gas surface density, circumgalactic medium of the spider web very nicely falls into the Schmidt-N configuration. The amount of gas that's there it's massive. It's about 10 to the 11 solar masses of gas that we see in the circumgalactic environment, if we believe the typical conversion. Still, this gas can easily be depleted by redshift 1. So there's still enough time for this whole system to form into a massive red and dead elliptical in the center of this protoclasm. So I'm going to show you now some new ALMA data we got for this object. We observed ALMA in CO4 to 3 transition and atomic carbon transition. Tune the receivers to get these two positions at the same time. So it's very nice now to compare this to the one transition of CO. It says something about the excitation condition of the gas, the carbon abundance of the gas. So I'm showing you here a few channel maps of the atomic carbon on this picture. And you can see it's actually very difficult to see, but there's actually, I overlaid contours of CO1 to 0 in these plots as well. What you see is that the atomic carbon is very strong on top of the radio galaxy, which kind of makes our interpretation a bit more tricky. But we see that the atomic carbon is basically spread on scales similar to what we see in the CO1 to 0 position. So what we did, we tailored the data heavily. We basically downweighted all the known baselines to get the total gas in this system. We subtracted this point source in the middle. So by doing that, we would get a first indication of the excitation conditions of the molecular gas in the spiral web, especially in the circumgalactic medium. And that's what you see here. So we got spectra for the circumgalactic medium in all three transitions. And I plotted here on a plot that shows on the horizontal axis the CO4 to 3 over the CO1 transition, which basically tells you something about excitation conditions. And here you plot the ground transition of C1 and CO, so it tells you something about the atomic carbon on it. Interestingly, all these points here, the small points, are ISM and local star-forming galaxies. Some of these larger points are ISM in high redshift galaxies, right? So you can see that the circumgalactic medium of the spider web, on average, has excitation conditions, carbon abundance, that really looks like the ISM and star-forming galaxies. So this large reservoir of gas that we see is not some huge diffuse or pristine gas reservoir. It really seems to be very similar to what you see in the ISM. So there must be a lot of feedback going on in this region. We're still not entirely sure what the nature is of this gas, but it must be enriched by stellar outflows, by galactic outflows. So yes, we find this large reservoir of gas driving them into the buildup of this entire region here. It fuels in situ star formation. It actually resembles the ISM of star-forming galaxies. So this is an enriched medium. And actually, if you compare this to some models, to me, the resemblance is quite striking. Here you see, for example, models by Narayanan and al., who show that at high redshift you can have galaxies coming together, creating a lot of feedback. There's a lot of metals being redistributed in the system, a lot of star formation going on, even in the medium between the galaxies. And this is really what we see in the spider web. So the whole region, in the old days, this would typically be a single submillimeter galaxy. And we're now starting to resolve all these different components. Now, we don't know much about these kind of reservoirs at high redshift. I just want to show you another example. This is work done by Claudia Ciccone et al. In 2015. And they found something very similar actually in a redshift 6 quasar, looking at the C+ transition. So what they found was a strong point source at the position of the quasar. And they also found an extended reservoir. And this is both C+ emission. So again, you see here this UV analysis. There's this point source in the middle, which gives you fluxional baselines. And there's this very extended gas reservoir, which is only really seen on the shortest baselines. So it's another nice example that at high redshift, these things could be more common than we think. Okay, so of course we observe some other systems. I'm going to show you another high redshift galaxy now, which gives quite some different results. This is called the Mammoth. It's one of the largest Lyman alpha nebulae that we know of. It's about 400 kiloparsec in diameter. And this is work that I did with Chen Kai and Sergio Prochaska. So they imaged all this in Lyman alpha emission. And what we did is we used the VLA in its most compact D configuration in order to trace molecular gas in this region. So that's what you see on the right-hand side here. The black contours are just the highest levels of the Lyman alpha emission. The nebula is actually much larger than that. But at the VLA you can see pockets of cold molecular gas in 4 regions that are associated with galaxies or with groups of galaxies. So I'm going to show you 2 of these detections in a bit more detail. So in the first region that you see here, we have quite a bit of molecular gas associated with the galaxy. But half of the gas is extended in the circumgalactic medium. There's this broad wing or possibly even an outflow or tidal feature that stretches into the CGM, really in a location where there's not a lot of emission in the HSTO2. So this shows you that quite a bit of molecular gas also in this system occurs in the CGM. In total, about 50%. Now, if you go to the central region, this is actually the most interesting region of the mammoth. What you see here is, again, cold molecular gas. But you see it's offset from central galaxies here. And this very much looks like what we saw in the spiderweb. The CO seems to follow this diffuse emission in the HST energy. So we only have one color HST energy here, so we're not exactly sure what the nature is of this diffuse HST emission. But it's clear that the gas is offset from the galaxies that are found in the circumgalactic medium. Maybe even more interesting, the velocity dispersion of the gas in the central region is extremely narrow. We have a velocity dispersion forward half max of only 85 kilometers per second. So this must be very cold and dynamically cold gas in the very center of the Lyman alpha area. So we believe that we trace this reservoir of molecular gas that's really pinpointing the center of the potential level of this nebula, and also the exact systemic velocity. When we compare this to the Lyman alpha, the CO is extremely narrow here. So in total, we found that also in the mammoth, about 50% of the molecular gas is distributed in the CGM. It's not as extreme as in the spiderweb, but we interestingly find this dynamically cold gas in the very core of the system. Now, interestingly, we speculate a bit that this could be related to what people have seen in the nearby universe. So there's studies, recent studies by, for example, Olivares et al., who found this gas associated with cold filaments in the very core of nearby cluster galaxies, brightest cluster galaxies, and really with velocity widths very similar to what we see in the mammoth. So it's interesting to speculate on this a bit more. I won't go into much detail here, but it's definitely interesting. People haven't seen this before with the high redshifts. So at the moment, I actually have a summer student working with myself and Ilsa Bjorn at NREO. We have beautiful ALMA data of the system. We have, again, 4-to-3 transition of CO and atomic carbon transition. And this student, Shane Bechtel from Arizona State University, he's actually at the moment looking at the ALMA data of the mammoth. So we can do a similar thing as we did with the spiderweb, really study in detail the gas, the cold gas in this region. Okay, so I've shown you a few nice examples. I'm going to show you another example here. And again, this is a system that shows a lot of molecular gas on large scale. I'll get to that. But again, a bit different story here. This is called the Dragonfly Galaxy. It's located at redshift 1.9. It's a spectacular system. It's actually a hyperluminous infrared galaxy. It happens to have a radio source. So you see here redshift plotted against starboard infrared luminosity. And these points here are all high-redshift radio galaxies. So you can see that the Dragonfly Galaxy is sticking above there. It's order of magnitude brighter in the starburst infrared luminosity compared to, for example, the spiderweb, which is around here. Interestingly, this system hasn't really been observed in detail. And the main reason is that most samples, high-redshift radio galaxies, observed at redshift 2 or higher, because that's where you get the strong Lyman alpha shifting into your bands of optical observatories. So this system has been ignored quite a bit, but we have beautiful ALMA data of this system. If you look in the central region, there's actually two disks, two merging galaxies. And this is work done by some student of mine from last year, Sophie Libowitz, who's done a very nice analysis of not just the molecular gas in the system, but also VLA imaging of the radio chain. So I'll explain you what's going on here. So we have these large merging disks. Here you see the rotation of the two disks. This whole system is only 4 kiloparsec in size, So it easily fits between us and the center of the Milky Way. But we have very high resolution ALMA data. And actually there's an AGN in this source. It blasts off a radio jet, and the radio jet actually brightens up where it hits the disk of the second galaxy. So it's a very interesting system. I can tell you much more about this later. At the moment we're looking at beautiful Keck cosmic web image data as well. You see a very interesting line alpha profile of this galaxy. And it's spectacular how far in the blue Keck can actually go. Now I don't want to go in details of this galaxy, but I do want to make a point here. So this is the typical data from ALMA that you get these days. I'm going to zoom out of this galaxy a little bit. I'm going to show you some ALMA data from cycle 2, where we didn't have quite the resolution yet. But again, this is the typical data you get in a millimeter machine. So you get CO there where you have star formation. We observed this galaxy with the Australian telescope configuration, which is a very simple 5-element interferometer at sea level in Australia. And we show all this gas pop up on 60 gigaparsec scales. So this is another example. If you look in the right way with the right instruments, you can start to detect all this molecular gas at large scales. So it's really another indication we're missing out quite a bit of molecular gas in the high-energy universe. I'm looking for a clock, see how I'm doing on time. Okay. I'm going to skip the next one. Okay. So just to give you an overview of what I told you up till now, I gave you an overview of cold molecular gas in some high redshift systems, basically massive Lyman alpha halos. And we see a lot of cold molecular gas in the CGM. But we see differences as well. In some cases, we see halos of gas. We see dynamically cold gas in the very center. We see tidal debris. So the nature of these reservoirs of cold gas is still unclear, right? But we know there's a lot of this gas that we haven't seen before. So we're doing some other work at the moment. We have some more ALMA data sets. And we're actually going to get data for a small sample to do with the VLA in 2019. So in this winter semester. Now one thing about all these systems that I showed you is that these are enormous Lyman alpha nebulae. These are typically the most massive systems in formation. So the question is, how about cold molecular gas around the more typical high redshift galaxies? Do we find evidence for that? I'm going to show you very quickly a few results of a large survey that we're doing with the ABCA. The PI is Hamid Denebauer, the IAC. And basically what this program consists of is mapping CO1 to 0 in two regions. One is a region where we image the spiderweb protocluster. So I showed you results of the spiderweb. This new study shows the larger protocluster environment. The other study is a field in the ALIS field, so that's more a field galaxy. So we can actually compare field galaxies with cluster galaxies and looking at the properties of CO1 to 0. Now I'm just going to show you two examples of these data. This is work in progress by Xiaoying Jin and Hamid Denebauer and the rest of our team. So look, for example, one galaxy here. This one is published, it's HD 229. In this particular galaxy, we actually saw a large disk as well. So again, this gives you an example that once you start looking in the lower transition of CO with compact array configurations, you can start to trace these large reservoirs of gas around even a bit more normal high redshift galaxies. One more example is this one here. And I'm sorry that you cannot really see the light blue here. There's gas all over the place. So this is work in progress, but it shows you that we're trying to push towards more normal systems at high redshift. Okay, so the last 10 minutes of this talk, I want to tell you a little bit more about the future of this work. I showed you a lot of results for the ATCA, for the VLA. Again, I mentioned the ATCA is a simple 5-element interferometer at sea level in Australia. Imagine you can observe these reservoirs of gas with a large 64-element interferometer in the gamma detector. Well, soon we will be able to do that. ALMA band 1 is expected to go on to ALMA in not too long time scale. With ALMA band 1, you can trace the ground transition of CO up to redshift 2.3. So things like the spider web, the dragonfly can be observed soon with ALMA in band 1. And keep in mind, we're pushing ALMA down to lower frequencies, so basically we get shorter and shorter baselines. So it's ideal for doing this kind of work around redshift 2. And on a bit longer time scale, we have the next generation VLA. So I'm going to show you a little bit on the NGVLA. The NGVLA is a conceptual telescope at the moment, but it's in the early design stage. And basically, the NGVLA will be able to observe the frequency regime between SKA and ALMA, so about 1 to 115 gigahertz. So you can basically trace the ground transition of CO throughout the entire universe. So just to give you a little bit of overview what an NGVLA can do, the concept of the NGVLA is that it's going to be a continental array in the US, replacing the existing very large array. It will have 244 antennas of 18 meter diameter, plus maybe a central compact core, like we see in ALMA, an ACA for short baselines. The NGVLA will have something similar. The redshift range will be between SKA and ALMA, and the maximum baselines will reach over about 9,000 kilometers. So the idea is we have a new VLA, a next generation VLA, extending over 4 to 5 states in the US, but with baselines connecting to the existing LBA baselines, the large baseline, which stretches from Hawaii to the Caribbean. So the idea is to get a much larger collecting area. Basically, the idea is to get 10 times more sensitivity, 10 times better resolution than either the current VLA or ALMA at the moment. So here you see a plot where you see the angular resolution against wavelength, and you can see that the next generation VLA will really trace a region where you can start to do really interesting new things. Like, for example, zooming in with terrestrial planet sound information. So it's not going to be a full talk on the NGVLA, but I'm going to show you very briefly the main key science drivers of NGVLA. So one is planet formation, really on terrestrial scales. Astrochemistry, NGVLA will be able to trace probiotic molecules in the ISM. What I'm interested in, evolution of galaxies. Of course, we can trace core molecular gas across cosmic time. I'm going to show you an example of that later. And pulsars. Pulsars in the galactic center will be able to test tests of gravity. There's a nice NGVLA science book for those of you who are interested in this. It's been put together by a large fraction of the community. And it was published recently in preparation for that, so 2020 data. There's still a few more very crucial hurdles that the NGVLA needs to take before it's actually becoming reality. But let's suppose everything goes as we hope. Basically, the early construction can begin as early as 2020, and full operations will be about a decade later. So I'm going to show you here, this is the concept of the main array of the NGVLA, which crosses into several states, maybe even into Mexico. I'm going to zoom in a little bit on the central region. So this is the region where we have the current VLA. If we zoom in a bit more, we see that there's actually going to be a very dense core to the NGVLA. And this dense core will consist of a whole lot of antennas with basically the same diameter as all the other antennas. But this will be ideal for low surface brightness work. So I'm going to show you one simulation that we Well, first of all, you can see that there's a lot more short baselines compared to what we have currently in the VLA deep configuration. And with this, you can actually trace this extended molecular gas on large scales. This is what I showed here. We've done this simulation with CASA. We took a model galaxy here, and Chris already ran this to simulate that run. And basically, what you get if you look at the intermediate baselines of the next generation VLA, you're going to be very sensitive to tracing all this emission, this cold molecular gas, on scales of star-forming regions and AGN regions. However, if you would just use the central core of an NGVLA, so the central 1 kilometer dense core, you should be able to see all this gas on much larger scales. So this is another way again that hopefully in the future we can start looking a bit more systematically for large reservoirs of cold gas at higher redshift. Okay, so let me conclude this talk. In the beginning I mentioned, are we missing a large fraction of molecular gas in the universe? I think the results I showed you is quite likely, yes, that's the case. But we need to look for it. We need to start using our instruments, pushing to low surface brightness sensitivities to really start investigating how much molecular gas we still need to observe at high redshifts. Because it probably plays a very crucial role in the evolution of galaxies in a high redshift universe. That's basically it. Thanks.